Okay, let us start. So we'll start with electrochemistry fundamentals because these fundamentals are responsible for the operation of your batteries, operation of your fuel cells, supercapacitors, heat harvesting devices, etc., etc. And if you take electrochemistry, electrochemistry is the study of the phenomena at the electrode-electrolyte interface. Electrochemistry begins when you dip an electrode into a solution containing ions. And your electrode has a lot of electrons and your solution contains a lot of ions. As shown in this image, you can see one phase contains electrons and the other phase contains a lot of ions. And you can see that electrons can cross this interfacial region, which is the fundamental act in electrochemistry. Electrons can cross this interfacial region, which is the fundamental act in electrochemistry. Remember one thing now. If the electrons leave the electrode into the solution side, if the electrons jump from the electrode into the solution side, definitely your electrode will acquire a positive charge. Yes or no? Yes. And what about the solution side? Solution side will acquire a net negative charge. Please keep that in mind. If the electrons jump from the electrode to the solution side, electrode will acquire a positive charge and the solution side will acquire a negative charge, a net negative charge. So you can see that once this charge transfer or electron transfer happens, your electrode-electrolyte interface will have a charge separation, which is the fundamental act in electrochemistry. Remember one thing that this interfacial phenomena of charge transfer or electrochemistry, what we call it as electrochemistry, is an interfacial phenomena. It happens only at the electrode-electrolyte interface. It is not in the bulk. It is not present in the bulk of the electrolyte. It is happening only at their point of contact, only in this region. It is not in the bulk. Therefore, electrochemistry is an interfacial phenomena. Why electrochemistry is an interfacial phenomena? For example, I draw an electrochemical cell here. Okay. I have some limitation in drawing it because anyway, it's an electrochemical cell. Okay. And I have kept an electrode in the electrochemical cell. This is an electrode. Okay. Suppose there is an ion far away from the electrode surface. It's a positive ion far away from the electrode surface. And on a time average scale, what will happen? The surroundings, this positive ion will see a spatially symmetrical world. It will be same this side. It will see the same atmosphere here. It will see the same atmosphere here. It will see the same atmosphere here. I'll just remove it a little bit far. Okay. This cell wall, I'll keep it a little bit far. On a time average scale, the surroundings of this positive ion will be spatially symmetrical. Everywhere it will be same, or the ion will see a spatially symmetrical world when it is far away from the electrode. So the ion will be very happy because there is nothing to worry about. Everywhere it is the same. What is there to worry about? What about this ion approaching the electrode surface? What about this ion approaching the electrode surface somewhere here? On the right hand side, you have the solution. What about the left hand side? On the left hand side, there is a giant electrode. You can see that this spatial symmetry is broken down now. the spatial symmetry experienced by the ion in the bulk of the electrolyte is broken down when the ion is near the electrode surface. On the right side solution, left side, a giant electrode. So what is the consequence of this spatial symmetry breaking down? The consequence will be ions will be terrified. Ions will be terrified. They'll be very afraid. Because throughout in the bulk, they were seeing a spatially symmetrical world, and suddenly they saw a kind of spatial asymmetry, and they will be terrified and they'll be anxious. And what is the consequence of this anxiety? You might have experienced whenever dogs chase you, the moment you become anxious, you get tremendous amount of energy to run. The moment you become anxious, you get tremendous amount of energy to run. So the consequence of any anxiety is the building up of tremendous amount of energy at the interfacial region on the electrolyte interface. So because of this anxiety, there will be tremendous amount of energy building up at the electrolyte interface. And that tremendous amount of energy will transform eventually into an electrode potential. This tremendous amount of energy at the electrolyte interface is responsible for what is called the electrode potential. And that electrode potential is the key, is the fundamental act, is the key for your battery, fuel cell, supercapacitors, or any device, solar cell you take. That is why electrochemistry is an interfacial phenomena. It happens only at the electrolyte interface. Nevertheless, having said that, when you look at this image, you will immediately notice that there are two types of electrochemistry. The first part is all about the ions in the solution. Therefore, that part is called ionics. And the second part talks about this electron transfer across this interfacial region. And that is what is called electrodics in electrochemistry. There are two types of electrochemistry. One is about the ionics. Second part is all about the electron transfer across the interfacial region. That is what is called the electrodics. And electrodics talks about the kinetics of an electron transfer reaction. Why kinetics? Because electrodics talks about how fast or how slow the electron is transferred across the interfacial region. An electron transfer is nothing but an electrochemical reaction. An electrochemical reaction inevitably involves electron transfer. Therefore, electrodics talks about the kinetics of an electrochemical reaction. Please keep that in mind. So the question is, what happens when you dip an electrode into the solution containing ions? What happens exactly when you dip an electrode into the solution containing ions? So you have two phases now. One is the metallic phase, the electrode phase. Second one is the solution phase. Let us look at the electrode phase, the metallic phase. From the band theory of solids, you must have learned that metals have overlapping valence band and conduction band. And semiconductors, there will be a small gap between valence band and conduction band. And for insulators, there can be a large gap between valence band and conduction band. These are all, you already know that. I don't have to talk about that. But the most important thing is electrochemistry is controlled by what is called Fermi level. Electrochemistry is centered around the Fermi level. What is Fermi level? Fermi level is defined as the top of the filled energy bands is called the Fermi level, or sometimes it is defined as the level where the probability of occupation is 50%. It is defined as the level where the probability of occupation is 50%. Basically, it is the top of the filled energy bands. For example, if you take two metals, metal 1 with the Fermi level like this, okay, you can see the Fermi level now, and take another metal with a Fermi level somewhere here. You can see that it is here now. And you can see the Fermi level of metal 2 is higher than the metal 1 now. What will happen if you bring them in contact? What will happen if you bring them in contact? That's my question. Metal 1 and metal 2. Metal 2 has a higher Fermi level compared to the metal 1. If you bring them in contact, what will happen? Something like this. The blue is the metal 2, whereas this left-hand side is the metal 1. So this is metal 2, and this is metal. I can't write properly. Very sorry for that, but I hope you can see that. The right-hand side is metal 2, left-hand side is metal 1. And if you bring them in contact, what will happen? Since the metal 2 has a higher Fermi level compared to the metal 1, what will happen? What will happen? There will be electron flow. What will happen is that there will be electron flow from the right-hand side to the left-hand side very clearly. What is the consequence of that? Electron is flowing from the right-hand side to the left-hand side. What is the consequence of that? The right-hand side will acquire a positive charge and the left-hand side will acquire a negative charge. So clearly, there is a charge separation. If there is a charge separation, there has to be a potential difference setting up at the interfacial difference. And this potential difference is often called as the contact potential difference. Okay, please keep that in mind. And we are not discussing about this here. This is just to refresh your memory about all these things. We are discussing about what happens when you dip an electrode into a solution containing ions. Electrode contains electrons and the solution contains a lot of ions. And I said metal has a Fermi level. Fermi level is the level where the probability of occupation is 50%, and electrochemistry is controlled by the Fermi level, top of the field energy bands. So metal has a Fermi level. Fine. What about the solution? Solution species also has a Fermi level. Why? Because it has a HOMO level, it has a LUMO level, and by definition, Fermi level is the level where the probability of occupation is 50%. Probability of occupation is 50%. So solution also has, the solution species also has got a Fermi level. And when you dip the metal into the solution containing ions, there are two possibilities. The first possibility is on the left-hand side. The Fermi level of the metal is higher than the Fermi level. See, the Fermi level of the metal is higher than the Fermi level of the solution species on the right-hand side. The Fermi level of the metal is higher than that of the solution species. And what will happen under such circumstances if you dip the electrode into the solution? Electrons will flow from the metal to the solution phase. What is the consequence of that? The consequence will be your metal will get a positive charge and your solution will acquire a negative charge. What about the opposite situation? That is shown on the right-hand side. That is shown on the right-hand side, where the Fermi level of the solution species is higher than that of the metal. In that case, electron flow will be reversed. What is the consequence? Consequence is solution will acquire a positive charge and electrode will acquire a negative charge. This is very, very important. So the consequence of dipping an electrode into a solution containing ions is nothing but there is a charge separation at the interfacial region. If there is a charge separation at the interfacial region, there has to be a potential difference at the interfacial region, because charge separation drives the difference. Charge separation is responsible for the potential difference. You all know that. So if there is a charge separation, there has to be a potential difference setting up at the interfacial region. And this potential difference is what is given by the famous Nernst equation. This potential difference is what is given by the very famous Nernst equation. For example, if you dip an electrode into a solution containing Fe2 plus and Fe3 plus, this is the electrochemical equilibrium. By IUPAC convention, we always write the reduction reaction, Fe3 plus plus electron going to Fe2 plus. And as we have just discussed just now, when you dip an electrode, there has to be a charge separation or a potential difference building up at the interface. That potential difference is given by the Nernst equation, and that is nothing but E is equal to E0 plus RT by NF into Ln concentration of oxidized species divided by the concentration of reduced species. Yes, you all know that. This is the famous Nernst equation, and you understood the origin of this equation now. It is nothing but the Fermi level equilibration and that potential difference setting up at the interfacial region is given by this famous Nernst equation. This is very important. This equation says two types of electrochemistry possible. This equation says types of electrochemistry possible. What is that two types of electrochemistry? Can anyone tell? Anybody from the crowd?
Yeah, oxidation and reduction.
No, I'm not talking about. There are two types of electrochemistry possible with this equation. Oxidation and reduction are inevitable in electrochemistry or batteries or fuels or anywhere. There are two types of electrochemistry possible. Look at that equation. What will happen if you adjust the concentration of Fe3 plus and Fe2 plus? If you vary the concentration of Fe3 plus and Fe2 plus, what will happen? What will happen? I'm asking you.
The electrode potential will change.
The E will change on the left-hand side. Am I correct?
Yes, sir.
So when you adjust the concentration of Fe3 plus and Fe2 plus, you can see that the electrode potential will change. And that is one aspect of electrochemistry. And that electrochemistry is called equilibrium electrochemistry. Where what you do, you adjust the concentration of solution species and thereby you adjust the electrode potential. That is what is called equilibrium electrochemistry. There is one more electrochemistry possible. What is that? It is exactly opposite of what you said now. It is exactly opposite of what you said now. I'm asking you, everybody, one more electrochemistry possible. This is very important.
So one is related to static and one is related to dynamic electrochemistry.
Yes, but what is that dynamic electrochemistry? Can you elaborate?
Means with
by applying external electricity and chemical species changes.
Yes. Who is this Ajay Ugale?
Yes, sir.
Very good. So the second aspect of electrochemistry is you vary the electrode potential. If you vary the electrode potential, automatically what should happen? The right-hand side should change. Yes or no? This side should change. Yes or no? And that is what is called dynamic electrochemistry. By applying the by changing the electrode potential, you change the ratio between Fe3 plus and Fe2 plus, and that is what is called dynamic electrochemistry. I have one more question here. What will happen if you increase the concentration of Fe3 plus?
E will increase.
E will increase. How do you know? From the equation?
Yes, sir.
You mean the E will become more positive, am I correct?
Yes, sir.
And if you increase the concentration of Fe2 plus, according to you, E will become more negative.
Yes, sir.
Because when you increase the concentration of Fe3 plus, this ratio will go up for sure. If this ratio goes up, electrode potential has to go up. If you increase the concentration of Fe2 plus, what will happen? This ratio will go down and electrode potential will become more negative. But my
Sir,
question is, yes.
It should also depend on the sign of E naught.
Even then, I'm talking about more positive and more negative with respect to that E naught. E naught can be negative. Okay, E naught can be negative, but when you increase the concentration with respect to that E naught, the electrode potential can be more positive and negative. That's what I'm talking about. All right. Is it clear?
Yes, sir.
Yeah. Now, my question is not that. My question is, can you explain this increase and decrease? The electrode potential becomes more positive and more negative just by looking at that equation. Fe3 plus plus electron going to Fe2 plus. Is that possible for you? That's my question. You don't need the Nernst equation. Is that possible for you? What will happen to the electrode potential? Will it become more positive or more negative just by looking at that equilibrium? Fe3 plus electron going to Fe2 plus. That's my question. It is possible. For example, if you increase the concentration of Fe3 plus, according to Le Chatelier's principle, the equilibrium will move to the right side. Am I correct? Equilibrium move towards the right side means what? There will be consumption of more electrons on the metal. This will be more and more consumed. Electrons are negatively charged. If they are consumed, what will happen? Electrode potential will become more positive. Very clearly. If you increase the concentration of Fe2 plus, equilibrium will move to the left-hand side. So there will be more and more accumulation of electrons on the metal. So electrons are negatively charged. So electrode potential will become more and more negative. That is how, that is another way of explaining it. Anyway, there are two types of electrochemistry: equilibrium electrochemistry and dynamic electrochemistry. Now, the most important aspect to discuss here is these electrode potentials are given in the electrochemical series. It is there in the electrochemical series. And if you look at the electrochemical series, you might have seen, you might know that sometimes it is 2 volt, sometimes it is 0.2 volt, sometimes it is 1 volt, like that. So you can imagine that this voltage is approximately you can take it as 1 volt. Not always 1 volt, but a few volts. So if you take it as 1 volt, okay, 1 volt. But this 1 volt is acting where? So where it is acting? It is acting at the electrode-electrolyte interface. What is the dimension of that electrode-electrolyte interface? The dimension of the electrode-electrolyte interface is a few. The dimension of the electrode-electrolyte interface is a few molecular diameters. It's a few molecular diameters, maybe 1 to 10 nanometer. It is a few nanometers. If you take it as 10 nanometers, what about the electric field strength? What about the electric field strength at the interfacial region? Electric field strength is nothing but the voltage divided by the distance in which that voltage is acting. What is the distance? It is 1 to 10 nanometer. And if you take it as 10 nanometer, if you take it as 10 nanometer, electric field strength is 1 volt divided by 10 nanometer. What is the value of this term? This is equal to, we are calculating the electric field strength at the electrode electrolyte interface. And the value will be 10 to the power 8 volt per meter. 10 to the power 8 volt per meter, because 1 nanometer is equal to 10 to the power minus 9 meter, which means the electric field strength, you can see it is 10 to the power 8 volt per meter. It is a huge electric field strength that is present at the electrode electrolyte interface. That is why your battery is very powerful. That is why your fuel cell is so powerful it can even drive an electric vehicle. That is why your supercapacitor is very beautiful. This intense electric field gradient existing at the electrode electrolyte interface is in fact the essence of electrochemistry. It is the basis of electrochemistry. Please keep that in mind. Now, this is the most important aspect to be discussed today. As I discussed earlier, when you dip an electrode into a solution containing ions, your one phase contains electrons, other phase contains ions, which we already know. So when you dip, one phase contains ions, the other phase contains the electrons. And suppose if I imagine that my electrode is like a tank. We'll change the color. If I imagine that my electrode is like a tank full of electrons. It's a tank full of electrons. Okay, because it contains electrons, free electrons. And if I imagine that my solution is another tank full of ions. Solution is another tank full of ions. Okay, this is my solution tank. It contains a lot of ions, positive, negative. Okay, this is my solution tank. So dipping the electrode into the solution means you are connecting the two by a pipe. There is a connection between the two, that's all now. So dipping the electrode into the solution means you are connecting the two tanks by a pipe. Well, at the end of the day, you should have a point of contact between the metal electrode and the solution. M means metal, S means solution, okay? So dipping the electrode into the solution means you are connecting the two by a tank. We are imagining, okay? So we are dipping the electrode into the solution means you are connecting the two by a tube. You are connecting the metal tank with the solution tank via a tube, as shown here. What will be the consequence now? The concentration of free electrons are very high on the metallic electrode. The concentration of free electrons are very high on the metallic electrode. So they have a tendency to flow in this direction. So they will have a tendency to flow in this direction. They will have a tendency to flow in the direction shown because of their concentrations are very high on the metallic electrode. What is the consequence? The consequence is very simple. The consequence, I'll just erase this, I'll put it in the top. Metal solution. What is the consequence of this electron flow? Your metal tank will acquire a positive charge. Okay, this is your metal tank side. And what about the solution's tank side? It will acquire a negative charge. I hope it is clear. But can I ask you, what is this positive and negative charge? What is this now? What is this you are seeing now? You have one plate positively charged, other plate negatively charged. What is that?
A capacitor?
A capacitor. But is that all? Is that all? That is not all, because there is a tank, there is a tube now connecting the two. Am I correct? That should not be forgotten. What is this tube now? Can you tell me? What is that?
Conductor.
Yes.
A conductor.
That
What is that tube doing? Look at that image above. It is allowing the passage of electrons. Am I correct?
Yeah, electronic
correct?
conduction.
So what is that? Electronic conduction. What is that?
Salt bridge.
No, yeah. You disappointed me. You shoot and kill me now. Electronic conduction means what? What is that? You said the positive and negative charge is a capacitor. Then what is a tube?
conductor.
A resistor, not a conductor. Yes or no? Yes or no? Conductor is nothing
Yes,
but a
sir.
resistor, rest. Yes or no? Because the tube is allowing the passage of electric charges, which means the tube is analogous to a resistor, which means your situation resembles like this now. You have one tank positive, the other tank negative, but in between you have a resistor. Yes or no? Or in other words, it will look like this. One plate positive, other tank negative. You can see there is a resistor in between that is nothing but, you can put it like this. The same thing. You see that? Do you agree or not? Everybody.
So not clearly understood.
Which one is not clearly understood?
You said that this is a resistor. How did you say that?
Because electrons, it allows the passage of electrons. So it's a conductor. It conducts electrons. So it has to be a resistor. If the other one is a capacitor, it has to be a resistor. If the moment there is an electron flow, there has to be a this conduction phenomena should come into picture. So there has to be a resistor. So that is what the tube means. Who is asking this question? I can't see the people. Hello?
This is Urmila.
Okay. Have you taken the electrochemistry course earlier?
No.
No. Okay. So you should have taken it. That is why you have this confusion. Okay. Anyway, but is it clear now, at least for time being, why there has to be a resistor? Okay. Now, when you go from the image 2, this is image 2 to image 3, my question is there any confusion? I want to know. This is very important. When you go from image 2 to 3, is there any confusion? Everybody? Arey bolo na.
No, sir.
Anybody? Any confusion is there? If no confusion, say no confusion. If there is confusion, please say that. It's important for me as well as you.
No, sir.
No, because it's the same thing. I put it in a different structure. That's all. Now, what is that you are seeing in? Sorry. What is that you are seeing here? What is this? What is that whole circuit? There is a resistor in parallel with a capacitor. What is that? What is that?
RC circuit.
Of what? Of what? RC circuit of what?
Interface.
Yes, when you dip the electrode into the solution containing ions, this is how your interface behaves. When you dip an electrode into a solution containing ions, this is how your interfacial region look like. Your interfacial region looks like this in terms of electronic models. In terms of electronic models, your interfacial region, there is a resistor in parallel with a capacitor. That is the model of your interfacial region. It's very, very important point. Now, what is the consequence of this? Presence of resistor in parallel with a capacitor. What is the consequence? That consequence is very interesting and it's very, very important. You all agree with me that when you dip an electrode into a solution containing ions, the electronic model is a resistor in parallel with a capacitor. The question we are trying to probe now is, what is the consequence of that? The consequence is very interesting. I'll show you. So your model of your interface is a resistor in parallel with a capacitor. Okay, the bottom one is capacitor, the top one is resistor. Suppose I apply a voltage across this circuit. Okay, this is a voltage. This is a battery. I'm applying a voltage across this circuit. Okay, please keep that in mind. This circuit means it is not simply a circuit. It is the moment you see the circuit, your imagination should be, this is nothing but your electrolyte interface. Keep that in mind. We are talking about the interface, but in terms of real world electronic components. Now, what am I trying to do? I am applying a voltage across this circuit, and I am plotting a graph between voltage and current. Suppose the voltage is along the x-axis, current I use the term I for the current along the y-axis. Remember one thing before we proceed. The voltage felt by the circuit we are talking about, the resistor and capacitor in parallel, the voltage felt by the circuit will change only when charges accumulate on the plates. It's a very, very important point. The voltage felt by the circuit will change only when charges accumulate on the plate. Because if there is accumulation of more charges, more voltage will be felt by the circuit. If there is accumulation of only less charges, only less voltage or less potential difference will be felt by the circuit. It's very clear. If there is more charge, more voltage, less charge, less voltage will be felt by the circuit. Please keep that in mind. Let us look at a particular case. Let us assume that the resistance R tends to infinity. It is very, very high. Just imagine. And you're applying a voltage. If the resistance tends to very, very high value, when you apply the voltage, what will happen? The resistance will not allow any charges to flow. The resistance will not allow any charges to flow across the resistor because it has a very high impedance or very high resistance. So what is the consequence? Charges will accumulate on the plate. Charges will simply accumulate on the plate because the resistance is very high. It will simply accumulate on the plate because they cannot pass through that resistor. And what is the consequence of this? Charges simply accumulate on the plate, which means the voltage felt by the circuit will change. What about the current? What about the current? I'm asking you.
Current will be 0.
Why?
Because there is no net current. The charge is not following.
Because of its very high resistance.
Yes.
But the charge is accumulating means the voltage will change. But resistance is very high, so there won't be any current flow. So there will be a voltage change without a current flow, which means the graph will look like this. Voltage is changing, but there is no current flow. You can see that. It's a horizontal curve, parallel to the V-axis. I hope this point is very clear. And this interface where the voltage is changing without a current flow is called a polarizable interface. It is called a polarizable interface. That happens when the resistance value is very, very high. What will happen if the resistance tends to 0? If the resistance tends to 0, what will happen? You're applying a voltage. If the
More transfer.
Say it again.
There will be more charge transfer.
Across the resistor.
Yes.
Yeah, who is telling this? I cannot see the people, that's why I'm asking. Hello, what is, so who is telling this
Shifali.
answer?
Sir,
Okay.
Shifali.
Shifali, okay. So what happens is that when the resistance is very small, tends to 0, and you apply a voltage difference across the circuit, since the resistance is very small, what will happen? The charges will leak through the resistor like this. And there is no possibility of accumulation of charges on this side. There is no possibility. Why? Because the resistance is very, very small. It can easily pass through the resistor. It can easily leak through the resistor. So there is no possibility of accumulation of charge on the, on the plates of the capacitor. So what will be the consequence? There is no accumulation of charge. In an ideal case, there won't be any accumulation of charge on the capacitor plates because charge is flowing across the resistor. If there is no accumulation of charge across the plates of the capacitor, the voltage will not change. Yes or no?
Yes, sir.
Yes, sir. Yes, but there will be
Current will change.
So there will be a current flow because charge is leaking across the resistor. So you can see that under such circumstances, your current voltage curve will look like this. You can see the voltage is almost constant, but the current is increasing. Voltage is almost constant, but the current is increasing when R tends to 0. And this interface is called a non-polarizable interface. A non-polarizable interface will happen when the resistance tends to 0. Under such conditions, there will be a current flow without a voltage change. Or I would say a non-polarizable interface resists any change in voltage across that interface. For that reason, a non-polarizable interface provides a constant voltage. Its voltage is always constant. For that reason, a non-polarizable interface should be, I'm asking you, should be or should function as, it provides a constant voltage. For that reason, a non-polarizable interface should function as, I'm asking you, should function as?
Reference electrode.
Reference electrode. Who told this answer?
Pooja.
Pooja, very good. A non-polarizable interface should function as a reference electrode. Why a reference electrode? Because the purpose of a reference electrode is to provide a constant potential. Yes or no? Yes or no?
Yes.
The purpose of a reference electrode is to provide a constant potential so that you can compare your other electrodes with that constant potential. For that reason, a reference electrode has to be non-polarizable. It's very important. Okay, these are all I think we have already covered. And your standard hydrogen electrode is one of the well-known non-polarizable interface. Your standard hydrogen electrode is one of the well-known non-polarizable interface because it is known to provide a constant potential. That is why it is used as a reference electrode. Now, what do you do? How do you measure your electrode potential with respect to standard hydrogen electrode? It's very simple. We will wind it up after talking about that. First, you construct your standard hydrogen electrode. These are all you must have studied when Professor Ballav taught you. I cannot talk about it again, but I'll tell you how to measure the voltage difference. It's very important. That's why. First, you construct your standard hydrogen electrode. So you take 1 molar HCl. Okay, HCl, and dip a platinized platinum electrode into that HCl. This is your platinum electrode. Okay. Sorry. This is your platinum electrode. And then bubble hydrogen gas at 1 atmospheric pressure. H2 gas at 1 atmospheric pressure, you bubble through this system. Your SHE standard hydrogen electrode is ready now. And you take whatever the electrode system you have. For example, you want to measure the electrode potential of Fe3 plus Fe2 plus, for example. Take that system. What happened? Doesn't go anyway. Take Fe3 plus Fe2 plus system. Okay, put the electrode into that system. Okay, connect your Fe3 plus Fe2 plus system to your SHE via a voltmeter. Connect the two solutions by a salt bridge. That is very important because the circuit has to be complete. Okay, now this is your electrode system. You are measuring the electrode potential. Okay, so now you have 2 half cells, one on the right hand side, one on the left hand side. Okay, and you are simply measuring the voltage difference between the two. And according to IUPAC convention, this is your right hand side half cell, this is your left hand side half cell, and this together constitute what is called the complete cell. And according to IUPAC convention, very clearly, the potential difference you measure in the voltmeter, E cell, is equal to ERHS right hand side minus ELHS, E left hand side. Okay, which means E cell is equal to E Fe3 plus bar Fe2 plus minus E SHE, because your left hand side happen to be SHE electrode. Under standard condition, this will become E0 cell is equal to E0 Fe3 plus bar Fe2 plus minus E0 SHE. And you know that SHE provides a constant voltage. And for comparison purposes, for comparative purposes, if you take E0 SHE as 0, if you take it as 0, just for comparison, you can take it as 0. It provides a constant potential anyway. And for comparative purposes, if you take it as 0, which one? The SHE electrode, if you take it as 0, this will become E0 cell is equal to E0 Fe3 plus bar Fe2 plus. What does it tell you? Whatever the voltage you measure across the voltmeter is nothing but your electrode potential. Whatever the voltage you measure across the voltmeter is nothing but the electrode potential of your electrode. And this way, what you do is that you change the right hand side electrode. You take platinum electrode, you take lithium electrode, you take potassium electrode. Like that, you change the right hand side electrode. Just measure the potential difference across the voltmeter. If you do that, you end up with what? You end up with what is called electrochemical series. This is how the electrochemical series is constructed. And for the electrochemical series, standard hydrogen electrode is the reference electrode. Everything is measured with respect to the standard hydrogen electrode. You just change the right hand side electrode. Lithium, potassium, sodium, silver, blah, 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 like that. And the most important message I wanted to give you here before winding up is, if you look at the electrochemical series, you see that some electrodes are negative, some electrodes are positive. And if you take a negative electrode, okay, if you take a negative electrode from the electrochemical series and take a positive electrode from the electrochemical series, pick one negative electrode from the electrochemical series and a positive from the electrochemical series. What is the meaning of negative in the electrochemical series? I should not use this language, but negative means it is my own language. Please don't try to refer it anywhere. It's my language. Negative means the electronic pressure is very high. It has a lot of electrons. That is why it is negative. Positive means it is deficient of electrons with respect to SHE. With respect to SHE, negative means it has more electrons. Positive means it has less electrons. It is deficient of electrons, which means if you connect a negative with a positive and connect the solution via salt bridge, what will happen now? Can you tell me quickly? We have only 2 minutes left.
Electron will flow from negative to positive.
What is the consequence of that?
The potential will generated.
We get electricity, yes or no?
Yes, sir.
Because electrons are flowing from the left hand side to the right hand side through the external circuit. External circuit is your surroundings. Your battery is your system, which means the system is doing work on the environment now, which means we are getting electricity. Electrons will flow like this. We get electricity. This is the principle behind any battery, any fuel cell, any supercapacitor, or any energy device. Thank you very much. Anybody can make any battery. I wind up here. If you have any question, you can ask me.